2,
What the heck?
1,
What are you doing?
go!
Okay, 3, 2,
Wait.
1,
Wait!
1, go. 1, start. Now first.
2.5.
No, good.
3,
2,
1, go. Welcome to the explanation of our rotational experiment lab. Here's the diagram of said lab and said apparatus. The arms are 0.1 meters or 10 centimeters on each side, or identical masses labeled little m. Here we see the rod which the arms are attached to, and the diameter of the rod is 0.01 meters or 1 centimeter. Here is a string connecting the rod to the pulley, which is connected to our hanging or falling mass, which is at a constant of 500 grams and is labeled big M. Now we should mention that the falling mass is hung at a height of 90 centimeters, or distance. So now we move on to our data table. Here we can see that our changing mass in grams is from 10, 20, 50 to 500. Now this changing mass is from the hanging mass, which is little m. And time is the time taken for the falling mass, big M, to fall against the hanging mass, which is little m, from 2.5 seconds to 21.4. And here's acceleration we derived from 2d divided by t squared. So here are the numbers. Move on to the graphs. So for this graph, this is the correct graph for the correct experiment if we hadn't done ours differently. So this is where the falling mass would change instead of the hanging mass, and the hanging mass would remain constant. Here on the y-axis will be acceleration, and on the x-axis will be torque, where slope is inertia to the power of -1, or inverse. Now from the equation we can derive it from, we will find that inertia will equal torque divided by acceleration, or inertia inverse would equal acceleration divided by torque. So this is the graph which would have been used if we had done ours the other way. But we did it our lab a different way, so we did it like this, with acceleration on the y-axis and inertia inverse on the x instead. And this will give us torque on the slope. So we found torque like this.